Astronomers have now confirmed over 5,000 exoplanets beyond our solar system. Many of them orbit in what's known as the Goldilocks zone, not too hot, not too cold, the narrow range where liquid water and potentially life could exist. Some are Earth-sized, some may even have atmospheres, and a few are starting to look eerily familiar. This isn't just a theory or science fiction anymore. Space agencies like NASA and the ESA, along with private companies, are already scouting these distant worlds, not just to study them, but to prepare for them. Because if Earth's trajectory continues, with growing population, resource strain, and environmental shifts, the question won't be if we need a second home. It will be, where do we go? And more importantly, are we already too late to get there? The quest to discover exoplanets, planets outside our solar system, has transformed our understanding of the cosmos. It wasn't long ago that the idea of other Earth-like worlds orbiting distant stars was purely speculative. But now, thanks to revolutionary advances in observational technology, we know that planetary systems are common across the galaxy. One of the most powerful tools in this search has been the development of space telescopes like NASA's Kepler and TESS missions. Kepler, launched in 2009, focused its gaze on a narrow patch of the Milky Way for nearly a decade. It detected planets by using the transit method, noticing the tiny dip in starlight when a planet crosses in front of its host star. This simple but powerful technique led to the discovery of over 2,600 confirmed exoplanets and thousands more candidates, many of which are located in the so-called habitable zone. The habitable zone, sometimes called the Goldilocks zone, is the orbital sweet spot around a star where temperatures are just right for liquid water to exist. And since water is essential for life as we know it, planets in this region become prime targets in the search for habitability. TESS, the Transiting Exoplanet Survey Satellite, followed Kepler in 2018 with a wider scope. Rather than staring at one section of the sky, TESS scans almost the entire celestial sphere, focusing on closer and brighter stars. This allows scientists to find planets that are not only potentially habitable, but also easier to study in more detail. These nearby worlds could become future targets for direct imaging and atmospheric analysis by next-generation observatories like the James Webb Space Telescope. Together, Kepler and TESS have revolutionized our understanding of planetary diversity. We now know of hot Jupiters, super-Earths, mini-Neptunes, and rocky planets of all kinds. But among these thousands of discoveries, it is the Earth-like ones, sitting quietly in the Goldilocks zones of their stars, that hold our deepest curiosity. Could one of them be the cradle of a second genesis of life? Mars, often called the Red Planet, has captivated humanity for centuries. From ancient astronomers tracking its motion across the sky to modern space agencies sending robotic explorers, Mars has always inspired awe and curiosity. Once believed to be a dead, barren wasteland, it has revealed a dynamic past and possibly a role in our future. This fourth planet from the Sun bears striking geological similarities to Earth. Dry riverbeds, ancient lake beds, and sedimentary layers suggest that water once flowed across its surface. The planet features polar ice caps, seasonal methane releases, and evidence of ancient volcanic activity. Mars may not be a frozen time capsule, it could be a world with stories yet untold. Signs of water, both past and present, are among the most compelling reasons for Mars's appeal. While it is currently cold and dry, Mars still holds vast underground ice deposits, and radar data has revealed possible briny water pockets beneath its surface. Rovers like Curiosity and Perseverance have found minerals that form in the presence of water, further supporting the theory that Mars may have once supported microbial life. NASA's Perseverance rover is exploring Jezero Crater, a site once filled with water. It carries advanced instruments to search for biosignatures and collect samples for future return missions. Meanwhile, China's Tianwen-1 mission has successfully deployed its own rover, Zhurong, showcasing a growing global interest in Mars exploration. What makes Mars a prime candidate for colonization is its relative proximity and the wealth of knowledge we've already gathered. We've mapped the planet's surface, identified ice deposits, and developed technologies for landing and mobility. But transitioning from exploration to colonization introduces new challenges: technical, environmental, and psychological. Mars's thin atmosphere, composed mainly of carbon dioxide, offers almost no protection from cosmic radiation and allows surface temperatures to drop well below freezing. Liquid water cannot exist on the surface without special conditions. Future settlers will need pressurized, insulated habitats. Lava tubes, large, natural tunnels formed by ancient volcanic activity, could provide shelter from radiation and temperature swings, making them attractive sites for permanent bases. To support human life, these habitats must be self-sustaining. Simulations on Earth, like NASA's High Seas in Hawaii and the Mars Desert Research Station in Utah, test conditions for long-duration missions. These include food systems, life support, team dynamics, and isolation protocols. Researchers are experimenting with hydroponics, aeroponics, and genetically modified crops to grow food in controlled environments. Some studies even explore treating Martian regolith to support plant growth. In situ resource utilization, ISRU, will be key. Martian settlers could extract oxygen from CO2 using technologies like MOXIE and harvest water from ice deposits. Fuel production on-site, possibly through methane synthesis, would reduce dependence on Earth resupply missions. These steps are vital for reducing the cost and risk of colonization. colonization. Energy will be another challenge. Solar panels can work efficiently near the equator, but are vulnerable to Mars's massive dust storms. Small nuclear reactors, like NASA's kilopower prototype, offer a promising alternative for consistent long-term power. Human factors are equally important. Communication delays of up to 22 minutes each way and launch windows every 26 months make real-time support from Earth impossible. Colonists will be largely isolated and must be self-reliant. Studies show that psychological resilience is as important as technical capability. AI companions, virtual reality, and recreation are being explored to support mental health in confined environments. Despite the daunting logistics, enthusiasm for colonizing Mars is growing. SpaceX aims to launch crewed Starship missions within the next decade, with visions of a permanent settlement in the longer term. NASA's Artemis program and planned moon base serve as precursors for a future Mars mission targeting the 2030s for the first human landing. Mars offers a testbed for technologies and strategies that could one day take us even farther, to the moons of Jupiter, Saturn, or beyond. But more than that, it offers hope, a second cradle for humanity, a chance to write the next chapter of our story, not just as Earthlings, but as a spacefaring civilization. Europa, one of Jupiter's largest and most enigmatic moons, may be our best chance at finding life beyond Earth. Despite its cold, desolate appearance, Europa hides a secret beneath its thick, icy shell, a vast subsurface ocean that could contain more water than all of Earth's oceans combined. This incredible potential has propelled Europa to the forefront of astrobiology and planetary exploration. What makes Europa truly captivating is the presence of tidal heating. As it orbits Jupiter in a slightly elliptical path, the moon experiences constant gravitational flexing due to Jupiter's immense pull. This mechanical stress generates internal heat, which prevents the ocean beneath the ice from freezing solid. It creates a stable, potentially life-sustaining environment, an ocean world warmed not by sunlight, but by the forces of orbital mechanics. Europa's surface tells a fascinating story. It's crisscrossed with dark, reddish-brown lines, fractures in the ice where subsurface water may have welled up and refrozen. These cracks, ridges, and chaotic terrain suggest that Europa's ice shell is geologically active. Some areas appear to be relatively young, possibly reshaped by material rising from below. This geological churn increases the likelihood of chemical exchanges between the ocean and the surface, a key factor for habitability. One of the most intriguing discoveries came from the Hubble Space Telescope, which detected plumes of water vapor erupting from Europa's surface. These geysers offer a unique opportunity. Instead of drilling through miles of ice, spacecraft could fly through the plumes and sample the material directly. If these plumes contain organic compounds or other life-related chemicals, they could provide powerful evidence of habitability or even life itself. NASA's Europa Clipper mission, set to launch in the mid-2020s, is designed to capitalize on these opportunities. Equipped with high-resolution cameras, ice-penetrating radar, magnetometers, and spectrometers, Clipper will perform dozens of close flybys of Europa. The ice-penetrating radar will map the ice shell's thickness and search for hidden lakes. Magnetometers will help infer the depth and composition of the ocean by measuring its electrical conductivity, and spectrometers will analyze the chemical makeup of the surface, including any compounds from the ocean below. These observations are not just data points, they are clues. If salts, organics, or sulfates are found on the surface, they could have originated from the ocean. Coupled with measurements of heat flow and ice thickness, scientists will be able to piece together Europa's inner workings. And if the Clipper mission detects active plumes again, it could attempt to fly through them to directly sample ejected material, searching for complex molecules like amino acids or lipids. Looking beyond the Clipper, space agencies are exploring even more ambitious ideas. Cryobots, robots that melt their way through the ice, could one day descend into Europa's ocean. Once beneath the ice, these probes could release submersible drones into the dark waters, equipped with cameras, sonar, and biosensors. These autonomous underwater vehicles would need to navigate pitch-black, high-pressure environments, potentially exploring hydrothermal vents where life could flourish. The ocean's interaction with Europa's rocky mantle is of particular interest. This contact zone could allow for geochemical reactions similar to those on Earth's ocean floors. On Earth, ecosystems thrive around hydrothermal vents, without sunlight, drawing energy from chemical gradients. If similar conditions exist on Europa, it's not just plausible that life could exist there, it's scientifically compelling. But even if Europa turns out to be lifeless, its study is still profoundly important. Understanding how subsurface oceans work, how they interact with overlying ice, and how they evolve over time gives us insight into the countless icy moons and exoplanets across the galaxy. It redefines what a habitable zone means, extending it beyond warm Earth-like planets to cold ocean worlds hidden beneath ice. Studying Europa can even shed light on our own planet's history. Some scientists believe life on Earth may have originated in deep-sea hydrothermal vents, environments, protected from harsh surface conditions. If Europa also harbors such environments, it could help validate those theories and guide our search for life on other ocean worlds, such as Enceladus, Titan, or even distant exoplanets with similar properties. Europa also sparks broader philosophical reflection. It challenges us to rethink what life is and where it might be found. It suggests that life might not need sunlight, dry land, or breathable air. In Europa's darkness, something utterly alien might thrive. Microbial organisms, or even more complex forms, adapted to an ecosystem cut off from the sun for billions of years. And that possibility forces us to confront a humbling truth. Earth may not be special. Life may not be rare. It may emerge wherever conditions are right, even in the hidden oceans of distant moons. If that's true, the universe becomes a much more vibrant, living place. Now, with exhausting the 2 potential planets that can support life in the solar system, let's take a look at exoplanets. Kepler 186f is more than just another name in a catalog of stars and planets. It is a milestone in humanity's ongoing quest to answer one of its oldest questions. Are we alone in the universe? Discovered in 2014 by NASA's Kepler Space Telescope, Kepler 186f made headlines across the globe because it was the first Earth-sized exoplanet ever found orbiting within the habitable zone of another star. Located about 500 light-years away in the constellation Cygnus, it marked a turning point, proving that planets similar in size and conditions to Earth might be far more common than we once imagined. The planet orbits a K-type main sequence star, smaller and cooler than our sun. Unlike stars that burn out quickly, K-dwarfs are known for their long lifespan, trillions of years, giving potential life forms ample time to evolve and flourish. Kepler 186f circles its star at a much closer distance than Earth does to the sun, completing an orbit every 130 Earth days. Yet, because its star is significantly dimmer, the light it receives is only about 1/3 of Earth's sunlight. Daytime on Kepler 186f would resemble an extended twilight, bathed in deep amber and orange hues, similar to Earth's golden hour just before sunset. This perpetual dusk-like environment opens fascinating questions. Could photosynthesis still occur under these lighting conditions? Would life evolve with different biological pigments to absorb red and infrared light? On Earth, some extremophiles and plants already thrive in low-light environments, so it's not beyond reason to imagine life adapting similarly on Kepler 186f. One of the most exciting factors about Kepler 186f is its size and composition. It's only about 10% larger than Earth in radius, suggesting it's likely a rocky terrestrial world rather than a gas giant. That size sweet spot is crucial. It implies that the planet could have a solid surface, gravity similar to Earth's, and a structure that might support mountains, oceans, and even a dynamic atmosphere. The possibility that Kepler 186f has a stable climate, complete with weather patterns and maybe even a hydrological cycle, is still purely speculative, but tantalizing nonetheless. If Kepler 186f does indeed have an atmosphere, its characteristics would dictate everything about the planet's potential habitability. Without one, it would be a frozen wasteland, its surface temperatures plummeting far below the freezing point. But if it has a thick, greenhouse gas-rich atmosphere, perhaps laden with carbon dioxide and water vapor, it might trap enough heat to sustain liquid water on the surface, a critical ingredient for life as we know it. Climate models suggest that with just the right atmospheric composition, surface temperatures could hover in the life-friendly range, despite the planet's distance from its dim star. Another intriguing aspect is Kepler 186f's orbital and rotational dynamics. Many exoplanets found around red dwarfs are thought to be tidally locked, with one side always facing their star while the other remains in perpetual night. However, due to its slightly wider orbit, Kepler 186f may avoid this fate. It could rotate similarly to Earth, giving it a regular day-night cycle and potentially stabilizing its climate over long timescales. That rotation, coupled with its position in the habitable zone, makes it an especially exciting candidate for further study. But here's where reality and limitations collide. Despite all of its promise, Kepler 186f remains shrouded in mystery. It's so far away and so faint that we can't yet study its atmosphere directly, nor can we confirm whether it has clouds, oceans, or even a protective magnetic field. We haven't seen the planet with our eyes, only inferred its presence by the slight dimming of its star as it passes in front. Even so, telescopes like the James Webb Space Telescope, JWST, and future missions such as LUVOIR, Large UV Optical IR Surveyor, and HABEX, Habitable Exoplanet Observatory, hold the potential to one day detect and analyze the starlight passing through Kepler 186f's atmosphere, if it has one. Scientists are particularly hopeful about identifying potential biosignature gases, molecules like oxygen, ozone, methane, or even chlorophyll analogs. The presence of any one of these would be exciting, but if we detect multiple gases that coexist in disequilibrium, like oxygen and methane together, it could be a telltale sign of biological activity, because these gases tend to cancel each other out unless something is constantly replenishing them. That something could be life. Beyond the science, Kepler 186f has also become a cultural icon, a symbol of the possibilities that await us in the stars. It's been the subject of documentaries, visualization, and sci-fi novels. Artists imagine its landscapes as dusky alien plains under a red-tinged sky. Writers dream of future astronauts setting foot on its surface, planting flags, and building domes. Engineers, too, are taking note, exploring interstellar propulsion systems that could one day deliver probes or nanocraft to such distant planets. Laser sail technology, for instance, could theoretically send tiny spacecraft toward nearby stars at a fraction of light speed. While Kepler 186f is still far beyond our current reach, the excitement around it fuels innovation back home. In the grand cosmic narrative, Kepler 186f reminds us that we are just beginning to scratch the surface of what's out there, and as our tools and techniques improve, this planet, and others like it, may very well help us answer one of the most profound questions humanity has ever asked. Are we alone in the universe? What do you guys think? Is Kepler 186f just a barren rock happening to be in the habitable zone, or is it a world teeming with life in forms we have yet to imagine? Leave it in the comments. Proxima Centauri b holds a special place in our cosmic neighborhood. At just over 4.2 light-years away, it is the closest known exoplanet to Earth, orbiting the red dwarf star Proxima Centauri, the nearest star to the Sun. Discovered in 2016 by the European Southern Observatory using the radial velocity method, this planet sparked enormous excitement in the scientific community, not only because of its proximity, but because it orbits within the habitable zone of its star, the range of distances where conditions could, theoretically, allow for liquid water to exist. This potentially habitable world is roughly 1.17 times the mass of Earth, suggesting a rocky composition rather than a gas giant. Its radius hasn't yet been measured directly, but it's likely similar to Earth's. It completes one orbit every 11.2 Earth days, circling incredibly close to its parent star, just 7 million kilometers away. For comparison, Mercury orbits the Sun at a distance of 58 million kilometers. This close orbit means Proxima b is probably tidally locked, with one hemisphere locked in eternal daylight and the other in perpetual night. But there's a twist. While this kind of tidally locked state might sound like a death sentence for habitability, it's not necessarily so. Many climate models suggest that with the right atmospheric conditions, heat could be redistributed around the planet. A twilight ring or terminator zone where the day and night sides meet could have moderate temperatures, stable climates, and potentially even liquid water. If life exists on Proxima b, this band of perpetual sunset may be where it thrives. Yet Proxima Centauri's nature presents a major hurdle. As a red dwarf star, it's known for extreme and frequent stellar activity. Solar flares, some thousands of times more powerful than those emitted by our sun, regularly bathe Proxima b in intense ultraviolet and X-ray radiation. These flares could potentially strip away any atmosphere the planet might have, exposing the surface to harsh radiation. Without a strong magnetic field or atmospheric regeneration mechanisms, habitability could be seriously compromised. This raises a crucial question. Does Proxima b have an atmosphere at all? If it does, what is it made of? Does it contain greenhouse gases that could help stabilize surface temperatures? Is there any water vapor or signs of biosignatures like methane or oxygen? These questions remain unanswered, but they're driving a new wave of observational campaigns. Scientists hope that instruments like the James Webb Space Telescope and upcoming extremely large telescopes, such as the ELT in Chile, may soon be able to probe Proxima b's atmosphere, if one exists, and analyze its spectral fingerprints. Despite its challenges, Proxima b has become a poster child for nearby exploration. Its relative closeness makes it one of the few exoplanets where interstellar missions could, in theory, happen within a human lifetime. That's where the Breakthrough Starshot project enters the picture. Backed by billionaire Yuri Milner and advised by Stephen Hawking before his death, this initiative proposes sending ultralight nanocraft to Proxima Centauri, propelled by massive ground-based lasers. These tiny probes, about the size of postage stamps, would travel at up to 20% the speed of light, reaching the system in just over 20 years. While these nanocraft wouldn't be able to land, they could photograph Proxima b from space, gather data, and beam it back to Earth. If successful, this would mark the first time humanity receives direct images from another star system, and it could provide our first real look at the surface of an alien world, maybe even one that could, under the right circumstances, host life. Long-term visions go even further. If future generations crack the code of faster propulsion, perhaps using nuclear fusion, antimatter drives, or theoretical constructs like the Alcubierre warp bubble, Proxima b may become the first interstellar destination for human explorers. While the engineering hurdles are immense, so too is the incentive. A planet just 4.2 light-years away, potentially rocky and temperate, could be the backup home our species one day needs. And what if Proxima b has no atmosphere, no magnetic field, no water at all? Even then, its value as a stepping stone cannot be overstated. Its proximity makes it an ideal testing ground for interstellar navigation, communications, and autonomous exploration. It might teach us how to terraform planets, extract resources, or build sustainable habitats under extreme conditions. Culturally, Proxima Centauri b has captured imaginations across the world. It's the setting for novels, the subject of documentaries, and a staple in discussions about about humanity's future in space. What makes it truly unique is how tangible it feels. It's not in some distant, unreachable corner of the galaxy. It's in our backyard, relatively speaking. We could feasibly reach it within a century, not thousands of years from now, but within the timeline of our descendants. Every new discovery about this mysterious world peels back another layer of what's possible. Is it lifeless rock, paradise in disguise, a failed experiment of planetary evolution? Whatever the truth, Proxima b stands as a monument to the power of scientific curiosity and the daring ambition to look beyond our solar cradle. In the end, Proxima Centauri b is more than just a nearby planet. It's a symbol of the next giant leap for humankind, and whether we find life there, colonize it, or simply study it from afar, it will forever change our place in the universe. As we reflect on these discoveries, it's essential to consider the challenges humanity faces in our quest for colonization. Technological advancements, biological health, and psychological well-being are all critical factors that must be addressed. Moreover, sustainable living practices and international cooperation will play vital roles in ensuring our success as we venture into space. The potential for life on other planets not only expands our understanding of the universe, but also invites us to think about humanity's future among the stars. As we continue to explore and innovate, we stand on the brink of a new era in space exploration. If you enjoyed this exploration, like this video and subscribe for more content about the mysteries of our universe. Together, let's keep asking the big questions and reaching for the stars.